Okay, let's begin. Starting a bit late, so let's get through it, because you know, we're in the end game now, right? If any of you saw it last night, keep your mouths shut. If you spoil it for me, I'll give you an F. I won't be able to see it till like Sunday.
Yes.
That's so. I'm off social media. Okay, let's talk about, we had some examples to do last time, areas between curves. So let's run through those examples. We'll do, and then we'll move on to something cool, another technique. Okay, so area bounded by sine x and x-axis on 0, pi. So sketch a picture of that. That's what the sine graph looks like on 0 to 2 pi, but we care about 0 to pi. So we care about finding this area right here. Now, that's just the area under the curve. We know that by definition. That is just going to be the integral. So here's the x-axis, that's one boundary of the shaded region, and sine x is the other boundary. So that's just the area under the sine graph. So this is simply going to be the integral from 0 to pi of the sine function. Integral of sine is minus cosine. Cosine of pi is minus 1, so that becomes plus 1, minus cosine of 0 is positive 1, so that's minus a minus 1. So 2 is the answer here. So that one wasn't so bad. The other example was the area bounded between y equals x squared and y equals the square root of x. So again, you can see what's going on here. I'm just sketching a little picture. So y equals x squared. Square root of x is like that. So the area we're talking about has to be bounded between both of them. It's going to be that guy. So of course, we remember from last time, to find the area between curves, it's going to be the integral from a to b of the top curve minus the bottom curve dx. Or right curve minus left curve dy, but we won't really explore things like that until calculus. How would we find the a and the b here? Yeah?
We set them equal to each other.
Right, it's where they intersect. So you set them equal to each other. For a and b, find the intersection. So, you can set the y values equal to each other. Now from this, you can probably see by inspection 0 and 1 are going to be the solutions, but if you don't see that, you can square both sides, and as always, you solve equations by bringing everyone to one side and factoring. That gives you x equals 0, and that would give you x equals 1. So 0 and 1 are the bounds for our integral. And you would also notice that the top is the square root function and the bottom is the x squared function. So the area I'm after is the integral from 0 to 1 of the square root of x minus x squared. That's x to the half, add 1 to the power, divide by the new power, add 1 to the power, divide by the new power. Plug in 1, bless you, 2/3 minus 1/3. 1/3 is the answer. So here the interval wasn't given to you, it arose naturally from just how the problem was set up. Find the area between these two curves, the intersection defined the interval for us. Any questions on this one? Got a third question. Area under that graph on that interval. I also want to sketch this graph. You realize in Calc 2 and definitely in Calc 3, your spatial awareness is going to be super important. You are going to want to know how to sketch things very quickly. And in Calc 3, you learn to sketch things in 3 dimensions. It'll be a little bit annoying when you first do it, but bite the bullet and learn it. It will make your life a lot easier because positional awareness is going to be important. So to sketch this, I'd of course find the intercepts and factor. So that basically means intercepts at 0, minus 2, positive 2. It's a positive cubic, so I know the right side is going up and the left side is going down. You can plug in numbers in here. If I plug in, say, minus 1, you'd notice here I would get a positive number. If I plug in positive 1 here, you'll notice I'll get a negative number. So the graph of this guy actually looks like that. And of course the area we care about is that. And again, that's just another area under curve idea. Don't have to worry about it. The bounds are already given to us. So we simply do minus 2 to 0 of this function. Now how do you integrate that function? Yeah?
Substitute out x squared minus 1.
You could get it by substituting x squared minus 4, but I wouldn't. I would just multiply out and apply the power rule. That being said, on the last quiz, there was a problem that it could work by a substitution, and I saw a lot of people attempt it by substitution, but they kind of had to force it to work in this very weird way. And when I wrote down the solutions to the quiz, I actually wrote out both ways of doing it. And one way was just to multiply out, and the solution was a one-liner. And then I actually wrote out what would happen if you tried to force substitution to work, and it took like 3/4 of a page. And so that's just to illustrate to you, again, what I try to say. Whenever you learn all these methods, always start with the simplest idea first. You always try to apply a basic rule before doing something as sophisticated as substitution. Now sure, if this were a square or a cube, then substitution immediately becomes worth it. But without that, it wasn't worth it here. And a lot of times you'll end up spending a lot more time on a problem because you're trying to get something sophisticated to work. Start with the basics. First thing you want to look at when you're doing an integral, can I apply a basic rule somehow? Can I rewrite this so I can apply a basic rule? That's always step one. It's kind of like when you're faced with a limit. You always try to plug in first thing. right? Don't try, oh, maybe L'Hopital's will work. No, see, can I actually plug in the number? That's always going to be the first step. Always try to go with the simpler things, only use something more sophisticated if necessary. And sometimes it can mean the difference between one-liners and 3/4 of a page to get to an answer. So I was looking through some of the scrap and I saw all the work that students were doing for like part 1 of the integration problems. Like, so this is an extreme waste of time. That being said, now I can plug in zeros everywhere. I get 0 minus plugging in a -2. 2 to the 4th, 16 over 4, minus, this will be 2 cubed, which is 8. 4 minus 8 is minus 4 times minus, that is positive. So that's it. Always try to get away with the easiest method first. This will always be true. I know you'll learn all these cool ways of doing stuff and you want to use them. No, use them sparingly. Use them when necessary. The last example was a bit of a thought experiment, because I didn't really give you any specifics to work out. Just want to make sure you can think about, you know how you want to be thinking about these problems. I had a graph like something like that, which I called f of x. There was another graph slicing through it here, which I called g of x. I labeled their intersections. And the goal was to find the bounded areas here. So how would you go about doing that? And could you write down a formula to actually find that area? Yeah?
We can do the integral from a to b of f of x minus g of x plus the integral from b to c of g of x minus f of x.
Right, so that was the formula. And the idea, again, that I want to bring to your attention is that sometimes you have these notions like areas top minus bottom. You have to be careful of how they're applied. You would notice here that the top is the f, while the bottom is the g. But notice over here, the role is actually reversed. The top is now the g, and the bottom is now the f. And it's things like these where sketching can really come in handy, right? Because sometimes in a single situation, you have roles being switched on you. You might have even 3 functions and only 2 of them are in play over here, whereas you need all 3 over there. So sketching is a very good way to actually come to terms with this. A lot of times you want to get this picture. They'll just say, okay, f is this equation, g is that equation, find the area between them. You'll construct a situation like this. Whereas without a sketch, it's probably going to be hard for you to know how to set up the integral. But now when we understand that we should always be doing top minus bottom, that brings us into the fact that we actually need 2 separate integrals to deal with this area. One for the first one where f is the top, and one for the second one where g is the top. And ultimately, that means our area would look like this. On the integral a to b, f is the top function. And we will add that to the area that we can find from b to c, where g is the top function. So that would be the formula to find the area here. You'd actually need 2 integrals. That's going to be super important later. So in Calc 2, you'll have situations where your point of view is going to matter. And you need to know which point of view, and this is of course in multivariable as well, which point of view is the better one. So you would have situations like this, where you have to find areas or probably something more complicated. Where you'd realize that if I were to look at it in the top versus bottom point of view, that intersection point marks a very important intersection, because to the left of that, the top is the parabola and the bottom is the parabola, Whereas to the right of that, the top is the parabola, the bottom is the line. Top and bottom changes. However, you would notice that if you were to tilt your head this way, you end up with a different kind of scenario. You can look at it as right versus left, and you'd realize that for the shaded area, the line is always on the right, and the parabola is always on the left. So if I think of it in a dx point of view, top versus bottom, I kind of need two integrals to deal with this situation. Whereas if I tilt my head and think of it in a dy point of view, I'd only need one integral to deal with this situation. So things like that will come up. We won't deal with it very much, but you need to know how to analyze regions kind of like this, knowing when roles might change versus not. And you can save yourself a lot of trouble, like instead of doing double the work.
So it will be left minus right?
Huh?
So it will be left minus right?
If I had the option, I would do that left minus right. So if I had, because obviously this, to maybe make it a little bit more specific, this would be like the positive radical of something, and this would be like the negative radical of that thing, right? And then this would be like my g. So I could find the area as, well, the integral of the positive radical minus the negative radical plus the integral of f minus g, or, and that's when I look at it in the dx way. Or I could look at it as solve for this in terms of the other variable, call this h of y, some function of y, and then call this one, I don't know, I of y, some function of y. And I could just find the area by doing, well, right minus left. And that would be one integral to get to the same answer. So this kind of way of thinking about a problem will be very useful very soon. I mean, I don't think I'll ask you guys where you need to do something like that in this class. That being said, there is something cool I want to talk about now. Recall, it's been a while, but we looked at something called the product rule. This told us how to differentiate a product of functions. Let's think of this in another way. Let's integrate the product rule. Now, the fundamental theorem of calculus tells me that integrals and the derivatives kind of kill each other. If the integral comes afterwards, you'll have a plus c at the end, which we all know about. But let's say ignoring that for the moment, the left side will become that, whereas the right side will become this. And for whatever reason, I can solve for this guy to obtain the following. And that happens to be a very important formula. But you won't see it like that in your textbook. You'll see it in a different way. Customarily, we use variables to represent these guys. And again, here you can think of this as f of x, g of x, and then we're doing f of x times g prime of x dx. And this would be, I'm just being lazy, I'm not writing down, but the variable you can think of as x. I can set u equals f of x and v equals g of x, so that using differentials, that would be my du, that would be my dv. And the formula becomes the following. The integral of u dv is equal to u times v minus the integral of v du. This is an important formula. And that's the one you would see in your textbook. It is called the integration by parts formula. It is what we get when we reverse the product rule. So remember, substitution was the reverse of the chain rule. Turns out we can also reverse the product rule. And we get what we call integration by parts. So called because you kind of set up parts to your function. Originally you want to integrate something that looks like this, but you think of it in parts. There's the f part and the g prime part. The f you consider to be the u, and the g prime you consider it to be the dv. And you kind of think of it as the one integral as two separate parts, and you kind of go through this form. It's called the integration by parts formula. So this leads us to 7.1, where we're going to talk about integration by parts. Another integration technique. A little bit more sophisticated than integration by substitution, as we will see. Has a lot more nuances. So this is now the next rung in the hierarchy. Face of the random integral, applying a basic rule is the first thing you're going to think about. Then, if you can't get that to work, think substitution. Then, integration by parts might be the next thing you think about for a typical integral, where there are no other warning signs that you will learn about in the next class. But integration by parts forms another way. One, you can recognize that it reverses the product rule. Right? Which we could figure out because the fundamental theorem of calculus would imply as such. And we kind of use it, you want to think about it as integrating products. So, substitution is when you wanted to integrate a kind of composite function, and here we want to integrate products. So this is like the equivalent of the product rule for integration. It's called integration by parts. And that's the formula. You need to have it memorized, memorize it however you can. One of my friends used to call it video here. I don't know why he said it with that intonation, but he said it with exactly that intonation. Oh, video, like VDU. U times V minus integral is VDU, and over here it's UDV. Memorize it however you can. I don't know of a nice mnemonic to apply here. If you have one, you can come up with one, just do it. I'll rewrite it here. Now, of course, the idea is the following. You want to compute this integral, however, it's really tough. And in theory, this integral would be easier to compute than that one. And some ideas of why the guy on the right would be easier could potentially be coming to mind. You can think, for example, if your u over here were an x squared, then your du would only be a 2x. You've literally decreased the power of the polynomial, right? You're ending up with an easier integral. Let's do a simple example, just a segue in here. Let's say you wanted to integrate that guy. X times e to the x. Now, if you're a good math student, the first thing you're going to think is, can I use a basic rule to integrate this? The answer is no. Can I simplify to use a basic rule? Not really. Okay, can I use substitution? Well, what would you substitute? U equals x, always a bad substitution. What about u equals e to the x? Well, u equals e to the x means that if you want to rewrite this x, you get an ln. Do we know the integral of ln? What's the integral of ln x? Do we know? I actually don't know the integral of L next. So substitution doesn't seem to be have much hope for us. We'll actually learn how to do that today, by the way. We don't know it yet. But I want you to know that you don't know. You know? I called my class earlier today, they thought, oh, isn't it 1 over x? No, that's the derivative. You don't want to be that kid who walks into the test thinking they know everything and then they get a bad grade. No, know what you don't know. Okay, so substitution also won't work here. At least not, we don't have the formulas for it. So integration by parts might be the next thing, and it happens to be a product. And I would notice that, hey, you know what? If I pick the u to be the x, the derivative is just going to be 1. That will make the integral on this side a lot easier. So I start there. Now u equals x is always a bad substitution, of course, but we're not doing substitution, we're doing integration by parts. The u and the v are different things. So I would choose the u, right? So here I'm picking the u, which means that the dv is the e to the x dx. So I can find the du, this is just 1 dx, and I can find the v, which is the integral of that, well that's just e to the x. And so now I'm just going to plug into that formula. So here, remember, I'm thinking of this as u and that as dv. The result should be u times v minus the integral of v du. My u is x. My v is e to the x minus my v is e to the x. And my du is just 1 dx. And that integral is easy to do. A basic rule we have actually helps us find that. Integral of e to the x is e to the x. And that's our answer. So the integral of x e to the x is that guy. X e to the x minus e to the x. Or, I don't particularly care, but you can factor out an e to the x if you want. And you can check. If you differentiated this, derivative of this would be product rule. You get e to the x plus xe to the x. Derivative of this is just itself, e to the x. So you have e to the x plus xe to the x minus e to the x. You just get xe to the x left over. So that actually works. Now, it might have seemed obvious to you that picking u to be x would work out here because the derivative is just 1. That will clearly make things easier. But it is not always obvious to make the choice. So let's actually talk about how to make the choice. And of course we have a mnemonic for this one. Mnemonic. It is called liate. I assume because lipte didn't sound right to some people. Well, you kind of memorize it vertically. And I'll tell you what it stands for. It stands for logarithm. I stands for inverse functions, like say a sine inverse or a tan inverse. A stands for algebraic. This is where that lipte joke comes from, because when they say that, they mean polynomials. Algebraic doesn't really mean polynomial, but that's what they mean when they say it here. T stands for trig functions. E stands for exponential functions. This is liate, and basically the idea is the guys higher in the list get to be u first. all the way going down. The guys lower in the list get to be u last. Remembering liate is how you will make the choice. You will notice in our original example, the x would fall under the A category, while the E will fall under the E category. E to the x falls under the E category. So here I have a product of functions. One of them is an A, one of them is an E. So according to liate, A gets to be the U. Set U equals to the x. Right? So that choice, if it's not obvious to you how to choose based on liate. This will always make the integral on the right side a nicer integral. It's very important. It's called liate. So integration by parts, you have the formula, which is this, but the formula, of course, depends on the choices that you're making for u and v. Liate is how you will make that choice. Let's do some more examples. Let's figure out this guy once and for all. What would be the integral of ln, the natural log function? Seems like it should be a basic rule. It's one of our fundamental functions. And yes, from now on, you should know this as a basic rule. We're going to derive it now with integration by parts, but I don't expect you to do that every time. Once we derive it, from now on, you should know what the integral of ln x is and remember it. Now, here we want to use the parts. You might realize that there's only one function present here, or is there? The trick with this, which you can use on multiple things, is to think of the parts as involving the dx. Right? Notice that how I was always writing this. So I can think of 1 dx as a part of the function. Don't think of it as ln x, but think of it as ln x times 1. In that case, the 1 would be an A, the ln would be an L, and according to liate, the L would get to be the U. So you would set U equals ln x, and you would set dv equals 1 dx. So you choose your U and dv like that. Also makes sense that obviously the U had to be the ln because you don't know how to integrate it, so you couldn't put it over there. The U is the guy you know how to differentiate very easily. The dv is the guy you know how to integrate. Here, your du would be 1 over x dx, and here your v would just be x. And so plugging into the formula, I want to do u times v. Keep writing down the formula until you remember it, minus the integral of v to u. U is ln x, v is x. So this is x ln x minus the integral of v times du. So that's x times 1 over x dx. Well, that just gives you 1 dx. That's a lot easier to integrate. Our basic rule can take care of that, power rule. So this is x ln x minus x. And so now we know that. It's very important. We shall now consider this a basic rule. This is something you just know now. So the antiderivative of ln x is x ln x minus x. You can figure that out with integration by parts. do another example. It's the integral of sine inverse. You'd use the same kind of trick. Think of that as being a 1 there. Notice that this is an I, the 1 is an A. In Leonte, the I comes first. So you would set your U equals sine inverse. Your dV would be 1. Derivative of sine inverse, that's 1 over the radical of 1 minus x squared. And V would just be x. So, applying our formula, U times V minus the integral of V du. And how would we do that one? How do we deal with this integral? Yeah?
Use substitution.
Substitution. So just as how when we're doing derivatives, sometimes you have to apply several rules at a time, can happen with integration. Here we're going to do several rules at a time. I would do a substitution. U equals 1 minus x squared. Du would be minus 2x dx. So my dx would be minus 1/2, 2x du. Ultimately, this would become x sine inverse of x minus, will now become plus the integral of 1 over radical u. So it'll become that guy. Add 1 to the power, divide by the new power. 2's would cancel. Now we do our back substitution. That's the antiderivative of the inverse sine function. It's not a basic rule, you have to remember that, but that's how you compute it. You can do pretty much any of the inverse trig functions this way.
On the test, when you're doing n boundary, do we do the substitution like in the steps, or like do we do that in the side? For the word, I'm sure.
You can do it on the side. You should show it though. Another example. No rest for the weary. Last example. X squared ln x. Spoiler alert, it's an integration by parts problem. How would you make the choice? What would your choices be? Who would be the u here? Sufi? ln. Right. So this is the L. This is an A. Leonte starts with the L. This guy gets to be first. So the dv ends up being the x squared. Now find the derivative of this one. Find the antiderivative of that one. And you plug into the formula. So this is u times v minus the integral of v du. So we end up with integral of x squared ln x. Power rule can integrate that guy, we would get x cubed over 9. So this is going to be another thing, another technique that you can use, and best way to get used to it and knowing when you would choose this technique, or you would use substitution, or you would do a basic rule. Just do a lot of problems, do a lot of drills, and just know you always go for the easiest one first. First try to do a basic rule, then try to do a substitution, then do integration by parts if those don't work. To segue into next time. How would you do this one? You can think about it, and we'll pick up with that guy next time. I'll show you something pretty cool that we can do. Stay dry, and I'll see you guys next week.